Okay, liquid nitrogen video number 2. Make sure you go back and watch video number 1 to know what's going on here. Kind of the same stuff, let my marshmallow cool back down. It's back to being nice and squishy. My rubber ball's getting there, maybe I can finally bend it and hold it in my hand. Now it's not as brittle anymore. A couple more things that I've had cooking while I got ready for the next video is just a straw. A straw is usually kind of bendy. Not so much anymore. Let's see here. If I actually, once again, trying to not to touch much with my hand. Nope, I didn't go fast enough. But before I was able to actually get my straw to shatter, things don't always work out, so that one's a fail. One more thing that I stuck in there while we were off camera, because it needs to cook a little bit longer. So here's a metal penny. I don't know if you can see that pretty well there. And even metal pennies become much more brittle after you add coal, after you steal all their kinetic energy. They compact, they shrink, and they become more brittle. Here's a direct demonstration. This is a pressure gauge hooked up to an enclosed metal ball. And the pressure gauge just measures the pressure inside of that ball. There we go. So what's going on here is the air inside of that enclosed metal ball is cooling down. The particles inside of that air are moving slower and slower and slower. And then the pressure goes down. So that's the relationship between pressure and temperature. If volume remains constant, when temperature goes down, pressure goes down with it. Pressure and volume, or pressure and temperature, have a direct relationship. When one goes down, the other one goes down too. And once again, Bill Nye showed you a video where we theorized that if we got to absolute zero, we would actually get to zero pressure because there'd be no motion. However, we're only at negative 195 degrees Celsius, so we're only able to get down to about 4. Let's see, is this in pascals? I think this is in pascals. Not important for the video. And then as I take it back out, I'll leave that over here. Although vapor, once again, just like with the dry ice, is just the air from the outside world having a little bit of moisture in it and freezing and creating a fog. And this pressure is slowly going back up as it warms up naturally in the air. There, it's up to 5 already, and it will keep going. Running out of cool demos. Let's finish this video up with one more. This one's not pressure or volume or temperature. It's just kind of a cool demo. Take physics and probably chemistry if you want to know more about this one. This is a superconductor. Yeah, superconductor. Had to check my name of that. Magnet. And the cool thing about superconductors, they're what runs on magnet trains and stuff like that, is that when you change their temperature, they can form some really unique magnetic fields. So I'm cooling my superconductor down there. And then I have a little magnet that I'm going to stick on top of it. And if I got everything working properly, not quite cold enough. So let's get it a little colder. I always got to get things colder to get this to work properly the first time. There it goes. So this is kind of difficult to see, so I'm going to zoom in. Sorry to those of you that get a little motion sick. Oops. It doesn't like when I zoom in that much. There we go. So one more shot of liquid nitrogen here. And I can get my little superconductor magnet here is actually floating. Whoops. There it goes. It's just floating there out in space. I can move it around. I can spin it sometimes. But it's literally not touching the ground. The physics behind this is kind of extraordinary. Do take physics or chemistry if you want to learn more. But for the purposes of my video, it's just a demo of, let's see if I can get one more angle where you can see that better. Oh, I had to move it because I'm afraid of liquid nitrogen. Where it's actually floating in the middle of the air. There you go. Watch out for